Welcome back for another exciting day of boot camp. Today I figured we'll have a counterpoint from yesterday, and we'll try to do everything at the whiteboard. Really just want to go through. Whereas yesterday we tried to cover an entire semester's worth of material in an hour and a half, today I would like to cover a lecture's worth of material in an hour and a half, so that's much more reasonable. And kind of point out, whereas yesterday was really all about the current state of what we know algorithms can do on large data sets. What today I want to point out is what can we prove about data sets using techniques from optimization. And in particular, we're going to prove one theorem and use that to kind of highlight a lot of the kind of core techniques and tools that people use commonly in this area. And it kind of will lead into some of the more general advanced techniques that Martin will talk about in the next two lectures. So hopefully we'll get acclimated before we kind of dive into all of high-dimensional statistics. So what I want to prove is one theorem today. Just the following. So let x 0 and Rn be a sparse vector. By that I mean all but s of the components are non-zero. Or zero, sorry, other way around. Non-zero would be worse. Let A be a m by n random matrix with, these are squeaky markers, I apologize, Aij, sampled from a normal distribution with variance 1 over m. Okay, so just a standard Gaussian random matrix. And we also have that m is greater than or equal to 1 plus epsilon times s, 2s log n plus s plus 1. I hate that plus 1, but it really just does make the formulas look nicer. Anyway, just leave it at that, plus 1. Okay, then x0 is the unique optimal solution of with probability and at least 1 minus 2n to the minus. I apologize for this one too. Okay, so now I'm in the way. I'll just stand aside from the theorem. This is what we'd like to prove. I think we should be able to do this in an hour and a half, in an almost elementary fashion. So this is kind of one of these standard results that you might see in compressed sensing. In some sense, this is the most fundamental, or not fundamental, but kind of like the most primitive compressed sensing result that you might prove. The idea is this. We're interested in finding a sparse vector from a matrix. And what you could think about here is that every row of this matrix is providing some information about the vector x. X is sparse. We want to say how many pieces of information do we need to find x using some kind of polynomial time algorithm. Okay, so what the algorithm we're using is minimizing the L1 norm, which I hope everybody here kind of has seen that that's what we do. Right? When you want sparse, you want L1. Yeah, Ravi, go ahead.
Are you assuming you've already gotten to a suitable basis that it's sparse?
I'm assuming that x is sparse. x0 is sparse, and just in the standard basis. So it's going to have s non-zeros and zeros everywhere else. We could do it in a different basis if you'd like, because we're measuring with a Gaussian random matrix,
yeah.
So it doesn't care what basis is sparse in, which is the nice pack. But I'm just going to assume that we know the basis is the standard basis. And the matrix we're measuring with is a random matrix. The entries are just generated at IID from the Gaussian distribution. And what we want to prove is how many rows does that matrix have to have? How many measurements do we have to take before we can recover the vector x0? And recovering it using just linear programming. So we want to just have the linear programming solution return the answer. Okay. And the number of measures we're going to need is a 1 plus epsilon, as we always. This makes it look like one of our standard theory results. We have 1 plus epsilon times 2s log n. And then that epsilon is basically going to propagate into the error probability. Okay. So this is kind of one of these standard things that we would like to understand and show today. This is not an optimal result. We could actually, I think if we want to make it optimal, we would have, actually this is why I have multiple pens. The optimal result would have this divided by s, log n over s would be what we'd like to get. We're not going to get that today. But to trade off to actually get a suboptimal result, what we're going to do is actually this proof will rely only on convex geometry and duality, which is kind of using these optimization tools. And then we'll need to know the large deviations of chi-squared random variables. And that's it. No random matrix theory, really. I mean, it's somewhat random matrix theory, but we're not going to look at things like what Joel Trock talked about on what was that, Tuesday? Seems like forever ago. The things that Joel talked about on Tuesday, we don't need anything particularly fancy to prove this result. The only kind of result we need to know, and if we had 2 hours, we could actually prove that result from first principles as well, is what are the large deviations of chi-squared random variables. Don't quite have time to do everything, but that's where we want to go. So questions about the statement or of where we'd like to go or anything?
We covered probability is 1 minus 2n minus something?
2n to the minus. This is an exponent. It's 2n to the minus that crud. So what can we say about this? First thing is that if s gets bigger, this probability gets a bit higher. So the worst case is when s is 1 for whatever reason, an artifact of some analysis. The other thing is as epsilon gets bigger, this gets small. The probability again gets closer to 1, has the properties you want. And I traded off having a nice looking bound for m in order having an ugly looking bound for the probability. What can you do? Okay. But I think the key thing to note here is that if n is huge, if we're in a high dimensional regime, that's 1. Even if epsilon and s are small. All right, any questions about the setup? That's our standard problem. This is kind of, and I would just want to note very quickly that this problem is like we were talking about how to solve this yesterday. We flipped the role of the cost function and the constraint. The thing we looked at yesterday was we put this down in the constraint, we put this up in the cost function. But morally, this is the simplest version. This essentially would be the case where we observe properties of x0 with no noise. Just want to understand what happens in that case, in which case we could flip the cost and the constraint.
Can we use a method yesterday to solve it? Because here it seems harder to evaluate what is a gradient of.
That's a great question. And so if I wanted to use a method from yesterday to solve it, I would actually flip these. I would do one of two things. I would either flip these or I would actually join this as a quadratic constraint to this problem. And for appropriately chosen multiplier, you can actually show that they're equivalent. We're not going to do that today, but yeah, that would be another way to solve it. There are lots of algorithms for, actually there was, Rob should know. There are like 4,000 papers on just algorithms to solve this. I'm not underestimating the number. I mean, it's ridiculous. There are like 4,000 papers on solving this linear program, which is crazy. It might be more.
50 of them are mine.
That's quite possibly true. It's quite possibly true. You do have one of my favorite ones, so that's something, right? Okay. Any other questions about that setup? So here's the first question. If we're just looking at a problem like minimize f of x subject to ax equals b, what does it mean? When does x star minimize this function over this set, or we'll say solve the optimization problem? When does x star solve the optimization problem? So intuitively, this is a very, now I'm over there. Wow, crazy. All right, so intuitively, this is actually a fairly simple answer to when it solves it. So basically, what is the feasible set? So the set of all x such that ax is equal to b is the same as the set of x star plus h, where h lives in the null space of A. Right? How about a standard linear algebra trick? So x star is the solution if f of x plus h is greater than or equal to f of x. Yes. For all h in the null space of A. Right. So, I mean, again, this is we're doing trivialities here, but it's kind of getting us to where we would like to be. So if I define a set T to be the set of all directions such that f at x star plus alpha d is greater than f at x star for alpha, for some alpha greater than 0. Oh, sorry, the other way around. Less than or equal to. Let's do it this way. So we want to say, what are all the directions that actually could make the function smaller at x star? We just want to say, when does t intersect the null of A equal the set of 0? So what we're asking is, when does a cone, which has some particular structure that's associated with f, so we have f, and then we're going to have all these directions, and make this smaller, t, and then we're going to have the set of feasible directions, A, the null space of A, and we just want to say, when do these two things intersect only at the origin? And that is every theoretical paper on compressed sensing ever written. We're just all we're doing is trying to prove, when does affine space intersect the cone at the origin. Okay, so there are many ways to do that. I think Martin is going to discuss some notions from statistics in terms of restricted eigenvalue theory. And there are ways to do this. We're really just kind of looking at things that look very much like minimizing notions of eigenvalues, but instead of having the set of all the things that we're allowed to look at in our Rayleigh quotient, we restrict that set to be some kind of cone. That's called restricted eigenvalue theory. I would like to do something a little bit more elementary than that and just look at what's called the subdifferential theory. So you'll note that the L1 norm is not differentiable everywhere. At 0 in particular, there's no gradient. So we kind of, but convex functions, and especially non-smooth convex functions, always have something that looks like a gradient associated with them at every point. And those are called subgradients. So we say that G is a subgradient of f at x if f of z is greater than or equal to f at x plus g transpose x minus z minus x for all z. Okay. That's a subgradient. And remember from yesterday, one of the definitions of smooth convex functions, a way to kind of characterize them, were ones where this approximation, where g was a gradient, was always below the function. So this is kind of just generalizing that notion to some other vector g. So we say maybe there's not just a gradient, maybe there's something else, and we call that a subgradient. So if the one problem without making slides is you have to deal with my terrible artwork here. Okay. Here we go. That's kind of pointy. Yeah, sure. So that's a function f, quite clearly convex. You can just look at it. And a subgradient at this point there's one. All right, there's a direction that's complete, a hyperplane that's completely below the curve and touches at that point. And then here's another one. And basically anything in between also works. Right? And so there's more than one. There's an infinite set of subgradients there.
That's an epsilon subgradient.
Well, here we go. Bear with me. There we go. Now it's a subgradient. Again, yeah. Easier to do in Keynote than on the whiteboard. I can't. I guess the real point though is it's much harder for me to fake that at this point, right? There's only one tangent curve here, and I would have a lot harder time. So we define something called the subdifferential. It's just the set of subgradients at it. And moreover, we're going to, so this is called the subdifferential. And df at x is equal to the gradient of f if f is differentiable.
How does this relate to the cone, the tangent cone?
So if I take the cone of the subdifferential, I get the polar cone to this. We're not going to talk about that. This is something that we're not going to be able to talk about in detail today because I did want to keep it elementary, but they are very closely related. It's essentially, if I take an element of the subdifferential and I take its dot product with something in this cone, I get a negative number. That kind of that's another way to characterize the subdifferential. Okay, so if it's smooth, then the subdifferential is a singleton. If it's not smooth, I might have something else. All right, and so if we did some examples, so we'll just focus on the one problem that we care about today, which is just the L1 norm. So what do I need to know? I need to know what is the subdifferential of the absolute value of x. Okay, so let's see if you guys are with me. If x is greater than 0, what is the subdifferential? Yes. And if x is less than 0, whoever said that, you could say it again. -1, that's good. And then, so the interesting case is that x equals 0. If I draw, there's my function. We basically have anything in between 1 and -1. Oh, sorry. It's an interval if x is equal to 0. So you have the whole interval from -1 to 1 at 0. Yeah, sure. No, that's fine. That's fair. That's better. That's better. Yes. Yes. I'm happy to do that. Happy to do that. Okay. So that's that guy. And there are really just two facts that you want to know about subgradients, and that really does almost everything. All of the subgradient calculus that you need kind of follows from these two facts. Well, maybe three facts. First one is really simple, is that if I take the subdifferential of a times f is just equal to a times the subdifferential at f. So if you scale the function, you scale the subdifferential. The second one is that the subdifferential of a sum is the Minkowski sum, which I don't know if I have a better notation for this yet, but that's fine. I'm just going to use this. So, and that I mean Minkowski sum. So what I really mean there is that you're taking the sum, but you have to take one element from every subdifferential, right? So you take one element from every subdifferential, sum them up. That gives you an element of the subdifferential here. Okay, it says Minkowski sum. And then actually the one, we're not going to use this today, but this is really, might as well pass on the most useful fact about subgradients, is that the subdifferential of f of x, well, let's say f is just the max over an arbitrary collection of affine functions. So I take the max over an index set of an arbitrary collection of affine functions. The subdifferential is the convex hull of all the AI where f of x is equal to AI transpose x. So basically anything that achieves a maximum is one of the gradient vectors, and you take their convex hull. And pretty much every time you need to calculate a subdifferential, you're just going to use one of these three rules in tandem with each other. So for the L1 norm, basically, it's pretty straightforward to see what the subgradient of the L1 norm is. So if I write here, where does it stop being visible? Okay, well, good. I'm going to write here. So the subdifferential of the L1 norm. So let's say that xi is not 0 for I in some set t, and xi is equal to 0 for I in the complement of t. Then the subdifferential is equal to, let's say, okay, well, how about this? V is in the subdifferential of this if Vi is equal to the sine of xi for I in t, and Vi is in minus 1, 1 for I in t complement. Yeah?
Sorry, could you interpret the condition that you wrote at the end? The last ones? Yes.
So basically what it's saying is that, so I have so here, what's a good example of a function that is a max of affine functions?
Every convex function.
Every convex function. That's a terrible example. Terrible example. I want a singleton from that set.
L1.
L1. Yeah, L1's a good one. But even better, let's do the absolute value. So the absolute value of x is equal to the max of x and minus x. Right? So if it's positive, what achieves the maximum? X. And then the vector there is just 1. So that's what we have. That's a singleton set. If it's negative, you achieve minus x achieves the maximum. And in that case, it's minus 1. And at 0, they both achieve the maximum. So you take the convex hull of 1 and minus 1. And that's exactly what we get. Make sense? Tim?
Clarifying question.
Yeah.
For the rule about Minkowski sums,
Yeah.
suppose you add abs x to negative abs x.
And you get
add
0.
exactly 0.
Yeah.
What happens to the Minkowski sum at 0?
This only works for convex functions.
Okay.
Sorry. I apologize. That's a great question. So subdifferential theory, if your function is not convex, you could do it, but it's weird. You have to do kind of like partial subdifferentiability because you don't necessarily have subdifferentials. Really the only way we're going to get affine spaces to lie entirely under the function if the function kind of looks like a bowl. That's the problem. So good clarifying question. I should have said that. Subdifferential theory only applies to convex functions. Is a useful. We'll just say that's true for the next hour. And Terry Rockefeller's not here, so I'm okay. I won't get into trouble. Michael is here. Uh-oh. Michael called me on something funny yesterday about what was it? Lower semi-continuity. It's all these things that I really kind of wish I'd never learned. But anyway, yeah, there are caveats that I am slightly glossing over that are technical. But for most of the applications that we're going to look at today, especially these simple things with L1, I'm kind of just trying to give as much detail as we need. Okay, so why do we care about subgradients? That's a good question. So I think the most useful fact about subgradients, I'm going to erase my terrible artwork, so that's gone. So x minimizes f, which is convex, if and only if 0 is in the subdifferential of f at x. I really don't want to call this a theorem, but might as well. I don't know what we want to call that. It's a very useful fact, and I guess we should call it a theorem because anything that follows immediately from the definitions is always a theorem. So there you go. So this follows immediately from the definitions because if we take any other z, f of z is greater than or equal to f at x. I'm copying from right above here, g transpose z minus x for any g that's in the subdifferential, and that's 0. So f of z is bigger than f of x, so x minimizes the function. And vice versa, clearly 0 is in the subdifferential if x minimizes the function. So life is good. That's kind of it's like that's the sign that your definitions are correct when your important theorems don't have to even prove anything. Okay, so that's kind of one of the motivations for where the subdifferential comes from. More interestingly, and kind of what we're going to need today, this is legitimately a theorem, is x minimizes f, again convex, over ax equals b z equals b, so we don't confuse ourselves, if there exists a lambda such that A transpose lambda is in the subdifferential of f at x, and ax equals b. It's one of these funny things when I teach convex optimization, and we use these are called the KKT conditions for the problem, for actually like for this problem, where f is now the L1 norm. I even do this, but the students always do this on the exam. You always forget to write down feasibility. So always forget to write. So it's not enough to just have the fact that you have stationarity of the cost. So basically that you can't move in the null space. And we'll prove this in a second. It's fairly easy. But the also important thing is don't forget x has to be feasible. Okay, so the proof of this is actually not hard, right? So basically, and I can do it in the remaining space on the board here. If h is in the null space of A, then f of x would be plus h, right? So this would be a feasible point, and that's going to be the only set of feasible points are going to be f of x plus h. We proved that already. Is greater than or equal to f at x plus A transpose lambda transpose h. And now that's 0. A transpose lambda was in the subdifferential. The difference between f of x plus h and x is h. A times h is equal to 0. And that's it. Okay, so that's I mean, again, it looks trivial, but this theorem is kind of the foundation of almost all the proofs in compressed sensing. This is what we're going to use.
I'm a bit confused about this.
Take that in. That's important.
So where did A transpose lambda go to 0 here?
A transpose. So I'll just write that up here. We have A transpose lambda transpose h, which is equal to lambda transpose A h, and that h is in the null space. Good question. Okay, so everybody with me so far? Any questions about subgradients or that optimality condition? This is going considerably faster than I thought it was going to. So I could take a pause. Michael said I was supposed to pause after half an hour, and we're going to have a... Okay, good. I mean, the thing that's weird about it is like these definitions seem tautological, and the proofs also seem so trivial. But it's like really powerful to get to the proof technique that we need. This is the theorem that we need, so memorize that for now. So let us return to the problem that we were studying at the beginning. We want to say, what is x0? All right, so here's going to be our strategy. We know that x star will be the minimum if we can satisfy, well, this will be satisfied automatically, right? I mean, we know that a of x0 is equal to a of x0. Good, that's easy. We just need to satisfy this condition. So what we need to find, so we're going to proof, oops, I shouldn't use the blue. So we need to find lambda such that, let's say V is equal to A transpose lambda. V I is equal to the sine of x0i if x0i is not 0, and Vi in absolute value is less than 1 if x0i is equal to 0. Okay. So this is what we want to construct. And most of these proofs are, this is one way to actually prove that these things work. We're going to construct what this is called a Lagrange multiplier, but we're going to construct a lambda that certifies optimality conditions. using a little bit of random matrix theory. Okay? Now, let's define a set T. So I kind of defined over there. I'm just going to define it again. This is just going to be the set of indices where x0i is not 0. This is sometimes called the support when you go and read these papers. And we're going to work with that support. So what we need is that A transpose lambda is on the set T is equal to the vector E. We'll have a vector E, which is equal to the sign of x0i on T. So the vector E is just going to be a vector of signs. It's going to be plus or minus 1s. It will have the length of that vector is S. And we want to prove that A transpose lambda in L infinity is less than 1 on the complement. That's just saying that all the entries are less than 1 in absolute value, right? The L infinity norm says that all the entries are less than 1 in absolute value. Okay, so this is what we're going to prove. Now, the way that these constructions almost always go is we solve this equation, equation EQ, and this is equation bound. We solve EQ just by using least squares. So interestingly, we use convex optimization to construct our multiplier. And a lot of the more advanced algorithms use more sophisticated algorithms than least squares. So for example, there is a very popular algorithm that was developed by some folks who do quantum computing for proving things about matrix completion. And this is kind of iterative construction for constructing, for approximately solving the solution. And they use stochastic gradient to construct lambda. They approximately solve this using stochastic gradient. So it's interesting that you use convex optimization to solve this equation first. We're going to use least squares. And then you take the solution you get out and you prove that this holds with high probability. Okay? So the first thing to note is that as long as M is this big, this will have a solution. Because A is random Gaussian, essentially means it's in general position, so not much to prove. So this will have a solution. A lot of the more sophisticated techniques, you even have to prove that you can solve this. But we can take it for granted because we're using the Gaussian ensemble. Gaussians make everything way too easy. Gaussians always make your life way too easy. So what is the least square solution of this equation? Let's first partition the matrix A. And I will just assume that the first S coordinates. I'm going to prove strictly less than 1. So one thing I am sweeping a little bit under the rug here is that to get uniqueness, you need strictly less than 1. But let's say that what we'll actually prove today is not that it's a unique solution, that's a solution. Uniqueness requires just a little extra. I mean, not much more. And if at the speed I'm going, I can actually show you what we're missing to get uniqueness. But yeah, you need this technically to get uniqueness. So I'm also going to rudely assume that AT are the first T coordinates, so we can partition the matrix like this. So the T is just the first S coordinates. Just permute the matrix so that's true. It's kind of like Martin calls this construction a dual witness. And it's kind of almost like we have someone who is the idea would be if someone told us where the support was, how could we certify that this solution was true to someone who didn't know the support? So that's kind of the idea here. Someone tells us where it is, we shuffle things so it makes the proof look nice, and then that will guarantee that the solution works out. Okay, so we have AT and AT complement. So basically, this guy is just saying that AT. Now I've noticed a terrible problem in my notation.
Yeah, T was a bad choice.
How about we'll use star for adjoint?
I didn't want to nag you.
You should have done. But that's okay, right? So from now on, we will use the adjoint as if we were over the complexes. Fortunately, we're over the reals, so this doesn't change anything. So there we go. So, hey, no, we're done. Those boards are done. Those are in the past. Those are in the past, man. We're going to erase that. Yes?
Are you sorting the columns or the rows today? Sorry.
Columns. So basically, this would be like, we'll have xt would be up here, and then xt complement will be down here. That's the part where we're not sparse and the part where we are sparse.
Those are the columns of A star, not A.
This guy No, this is the columns of A.
Okay.
And what we're going to look at is those columns adjoint with lambda. So lambda lives in Rm. And AT is M by S. So it's overdetermined in particular, but so that allows us to do the transpose this way. Okay? So what is the least square solution of, so Jim, what is no, sorry, we don't, AT star lambda equals E. And actually, let me move to the next board. We want to minimize now the transposes are completely in the past. Erased from the record. We want to minimize.
Everything is recorded.
Huh?
Everything is recorded.
Uh-oh. Nobody told me that. We want to minimize the norm of lambda subject to AT transpose lambda is equal to E. And I'm going to just tell you the answer and then exercise. Lambda is equal to AT times AT T inverse E. It's the pseudo-inverse. You can actually do this out explicitly if you were to solve the KKT conditions, actually. So exactly the proof that we had before, find me the solution to the KKT conditions. You would let's just square it, so we're really doing least squares. And then that thing that I just erased, use that will prove that this is true. Okay? And now you could also very readily check for yourself that it works, because if I multiply through by AT star, everything goes to the identity matrix.
Ben,
Yes?
what gives you the condition that AT is
So A is generated as random Gaussian, and it's kind of I'm using something that is kind of obvious, but it's also not as immediately obvious. That matrix is in general position. So anything where I have more rows than column will have full rank. Will have full row and column rank.
It's a deeper question, right? Because in this where the restricted isometry and all those things eventually come from.
Well, no, you need something stronger for restricted isometry. Really, here we're just saying general position. I just need invertible. I don't need anything. I don't need that this is actually well conditioned. That's something stronger. And Martin, are you going to talk about restricted isometries or?
Very briefly.
Very briefly. So go with that in more detail.
Conditioning is a numerical issue, right? But
well, restricted isometry is just local conditioning.
yeah, but I mean, isn't it related to rank? I mean, so ultimately, if this were not full rank, your proof wouldn't go through, right?
Correct.
So
Correct.
In a sense, that's the condition you want, right?
Correct. And actually, I think one of the when you're doing something other than Gaussians, you actually have to do a little bit of work to prove that this is actually invertible. And essentially, the matrix Bernstein inequality is a really simple way for a lot of random matrices to prove that this system has a solution. And that's kind of why you would go through all the trouble of dealing with those large deviation inequalities. For us today, because it's just Gaussian, you just say, well, it satisfies no polynomial equations. In particular, those minors all have to they can't be zero, they can't vanish. And so we just use the property that we have this nice real value distribution to kind of just sweep that under the rug and say, hey, of course that's invertible. Yeah?
What is your intuition? Why is that particular solution for lambda actually has a good chance of satisfying?
That's a wonderful question. So this was the earliest I've seen someone derive. Now, Rob, you could correct me on this. The earliest I've seen this particular ansatz. This is one of these standard this seemed like a good idea and we ran with it. So this is, which I guess is what an ansatz is. This ansatz I think is attributed to J.J. Fuchs, who's a signal processing guy who's done a lot of stuff on L1. And it's kind of at the heart of what is essentially every compressed sensing paper from 2004 to 2009 used an argument like this. Is this the only way to do it? I don't know. But it is a really interesting thing that with even the more advanced methods. Actually, Gungbo, do you have anything to add to that? Why do we just do least squares?
I think it is the whole values of the field that
Yeah. Yeah.
we want to make
Over here, right? So how can we do it? It is a very weird thing. It's a very weird thing, especially in this case, where basically on the we're just trying to. What we'd really like is that the whole lambda that comes out, or A transpose lambda, has small norm, small infinity norm. This matrix, one of the nice things, and we're going to get to this right now. If you look at this matrix, these two submatrices in the Gaussian ensemble are completely independent. They're statistically independent of each other. So essentially what you want to do is just fit this to be kind of as small as we possibly can. You do that by least squares. There probably could be other constructions. It's convenient. I guess it's another thing that you might want to say is like the first thing you might try would be to do the more Penrose pseudo-inverse and see what happens. But there's no reason that this is the only way to do it. And I'm sure that there's, I think, a lot of stumbling blocks. Certainly in the first matrix completion paper that I wrote with Emmanuel, one of the big stumbling blocks was we just were trying to do this, and that ended up being 50 pages of nonsense. I mean, it was crazy. So it's really like forcing. It's like, you know, we have one idea, and we're going to force that hammer to beat up on everything. So maybe that could be the answer. Lack of creativity. That's why we do this. I wish I had a better answer to that, but we'll stick there for now. How about that? Any other questions about this construction? Okay, so we are actually, I can put that page down unless you guys are, yeah, go ahead.
Where does lambda live?
Rm.
Okay.
Rm.
That equation is okay.
So A has m rows and S.
The equality constraint.
So AT is m by S.
Okay.
AT transpose is going to be S by m, and then so forth. Yeah, I mean, you got to chase dimensions too. Yeah. Just
thinking an argument from your lambda. Could you just say by coordinate duality there must exist lambda? Because A is full rank, it must be unique.
A is not, lambda will not be unique.
If A is full rank.
A is not full rank. Oh, sorry, A is full row rank, yeah. But that doesn't necessarily mean that you have a unique dual solution. Actually, in fact, we definitely don't have a unique dual solution.
Well, then you have a problem.
Well, this is a different, this is different, right? This is AT. This is only a submatrix. You think, yeah, it's a great question because it's a convenient construction. Actually, so one of the problems where this is actually considerably easier to look at is when you look at the lasso, which is something that we do in statistics. So when we look at the statistical problem, actually in that case, the dual solution is unique. And so you can just write down the dual solution and prove it has all the properties you want, and that's at the heart of some of Martin's work. Proving that it has the properties you want is not easy, but still, but at least you have a unique dual solution. Here we have a lot of dual solutions. We have to pick one, and this is the one we're going to pick. I haven't even proved this dual feasible yet. I've only proven half of it. So we satisfied EQ, and now we got to satisfy bound. Let's roll with it for now, though. Let's see where it goes. Okay, so we satisfied EQ. We got this out of the way. Now the question is, how do we satisfy this dude? Okay, so let's look at that matrix. What is that matrix? This guy we'll call Z is equal to AT complement adjoint AT inverse E. We want to prove that the absolute value of Zi are less than 1 for all I in T. This is kind of the remainder of the proof, or at least with high probability over the ensemble. Fair? How do we do that? So the first thing, and I mentioned this before, this matrix and this vector are completely independent in the Gaussian ensemble, which makes the Gaussian ensemble very easy to deal with. So what we might want to do is say, what is the norm of this guy? If we condition on the norm of this guy, then this guy's Z is just a Gaussian random variable. And then we're just bounding the magnitudes of a Gaussian random variable. That's very easy to do. Right? I mean, Tail bounds for the Gaussian are pretty easy. Okay, so that's what we're going to do. What do we think the norm of this guy should be? Step one. So well, let's call this vector. We already have a name for it. It's called lambda. There we go. Life is good. That vector has a name. That's called lambda. So what is the norm of, what do we think the norm of lambda should be? All right, so here is where so we're not going to, this would be another place where random matrix theory would often come in if we didn't have the Gaussian, but we're going to use something nice about Gaussians. And I'm going to claim that the norm of lambda squared is distributed as S times M times B11, where B11 is the 1,1 entry in an inverse Wishart matrix with m degrees of freedom. Okay, what do I mean? Really complicated. What do I mean? Let's actually just write it out. What is lambda? What's the norm of lambda squared? Well, you get a bunch of cancellation. The norm of lambda squared is just equal to E transpose of AT inverse times E. Matrix, a lot of things cancel. Okay, so this is just a Wishart matrix. A Wishart matrix is just the outer product of two Gaussians. Okay, and we take its inverse, and then we're taking E transpose E. The nice thing here is that the Gaussian ensemble is, okay, again, what are we using about the Gaussian ensemble? It's completely isotropic. It doesn't care what direction the vector points in. So this is a vector of norm root S. So when I multiply this through, this is S times the first entry. This is identically distributed to S times the first entry of B11. The M comes out because we're assuming that Aij is distributed this way. That's it. So it's just basically, so now we just have to control the large deviations of the first entry of an inverse Wishart. Whew. Complicated. So here is something that is just totally remarkable. And it's actually it's a very easy thing to prove. Maybe we'll do it at the end if people really want to see it. But this is identically distributed to an inverse chi-square with m minus s plus 1 degrees of freedom. It's super cool, very unexpected, but that's like so controlling the large deviations of chi-squares is easy. That's another thing that we could, if we had time, we could prove the Chernoff bound for that guy in like 4 lines, and that's all we have to rely on. That's the only large deviations we need. Now, why is that true? So basically, the way that you would prove that that's true is you would write out the matrix inversion lemma for what this guy looks like, and you'll quickly see that it's the projection of an m-dimensional vector onto a m minus s plus 1 dimensional space. Everything's Gaussian, so everything remains Gaussian, and then you take its norm. We can do that out in detail, but just trust me. Okay, the proof is just what I said. Okay, so that's really the hard part here is just writing this in some convenient way. So what's the probability that the norm of lambda squared exceeds, let's say, a bound tau? What's the tail bound? And this one we are just going to copy from, or even better, let me do it out so we have a nice form for what we think it should be. Because it's a chi-squared, and because we're normalizing, we're going to say, what's the probability that the norm of lambda exceeds ms, which is that multiple that we got from here, divided by the degrees of freedom, m minus dt plus 1. And let's just take our extra degree of freedom minus t is less than or equal to exp. Sorry, I call it s. S plus 1 minus t. Oh, sorry, not t. Minus 1. Okay. I'm happy with that. All right, so this one, this is just again, something that not going to derive today. There's a lot of references for this one. This is just a standard. All we're using is tail bounds for the chi-square distribution. So, yeah?
So there's an MS factor also, right? When you say lambda squared is like the inverse chi-squared?
Is ms times the inverse chi-squared. Yeah, good. And this guy kind of is just, you could copy from like a survey paper by Massar, any book on concentration inequalities. It's kind of one of the first ones you can do. You could derive it directly from the turnoff bound. All right, so any questions about that? Because this is the hardest part of the argument. We just have to control the norm of this vector, lambda. And the way we do that is in the case of the Gaussian ensemble. I mean, in all of the proofs that you do in compressed sensing, the first step you have to do is compute the inverse, and then you have to control the bound. You can control the bound either by controlling the norm of this matrix, which is typically what you do, but we're using the isotropy of the Gaussian to control the whole vector at once. And when we just do some calculation, it turns out that we don't really need anything particularly fancy. We don't need Marchenko-Pasteur. We don't need matrix Bernstein. We just need to understand how chi-squares work. Questions about that? You guys are hanging in there because we're almost done, so we can fill in all the gaps that I'm skipping. That's good. Let me erase this, and we'll finish the proof. So the last step is conditioned on the fact what is the probability that the absolute value of zi exceeds 1, conditioned on the fact that the norm of lambda is less than that. So what's the probability that one component is too big? Well, this is exactly the same as the probability that the magnitude of, let's call it W, is greater than 1, where W is normal, and I want to make sure I copy this right, because the M cancels with variance. So it's, like we said, basically once we condition on this vector, now we just have a Gaussian matrix times a vector, and hence we just have a Gaussian random vector. All we have to know then is what the mean is and what's the covariance. The mean is 0. It's actually, now we're looking at one component, the mean and the variance. The variance is this. And so what's that bound? What's that bound?
We're just wondering if it's equal or less than or
Equal. Equal. Because, huh?
But the bound on lambda is inequality.
Oh, okay, fine.
Well, but yeah, it's still fine.
I think it's still fine, right?
Well, no, I'm just saying it.
Oh,
because, well, the worst case would be when you hit.
I think you're right. So we say less than or equal to, though. You're right. Because it's an inequality on the other constraint. You're right. Fine. Less than or equal to. We'll take the worst case. All right, and then we'll do, this one don't need anything fancy for either. It's just the probability that that's bigger than 1 is just the minus 1 over 2, sorry. Just the variance over 2, right? E to the minus variance over 2. Okay, so let's put it together and then you can pester me. So we want to say when is x0 not the unique optimal? When does our thing fail? When does our construction fail? We're going to upper bound that by the probability of this thing not actually being a good multiplier. So the probability that lambda is not a good multiplier is just the probability that A t complement lambda infinity is bigger than 1. This is less than or equal to n minus s times x of minus m minus s plus 1 minus t over 2s. So it's the probability of this conditional expectation not being true plus the probability of the thing that we're conditioning on not being true, which is x of minus t squared over 4 m minus s plus 1 close parentheses. Okay, so this is the probability that our construction doesn't work. Again, it's the probability that conditioned on lambda having well-behaved norm, we have a deviation in the size of these zi's, plus the probability that lambda fails the condition that we're conditioning on. It's these two bounds. I claim that if you plug in t, and I don't want to do this, so we're not going to do it, dt plus 1 is epsilon s log n square root of 1 minus 2s epsilon over 1 plus epsilon minus 1. This proves the theorem. So the probability of failure, this guy, is basically achieved by plugging in this value of t. How do we get that value of t? We set these two terms equal to each other. I don't know. We can do something else. And that will give us this expression. Okay, so that's the proof. So let's step back and go through what were the steps. The first one was understand basically what are good, with no knowledge, what makes a good certificate that we have the right answer. What are the combinations we need? We needed just basically this dual solution. We needed something to satisfy the KKT conditions. To satisfy them, we wrote down the KKT conditions. We got equality constraints and inequality constraints. We plugged in our equality constraints, checked those off, life was good. And then we proved the inequality constraints by basically just satisfying this with least squares. To prove the inequality constraints, we were in this. So there are two things that are difficult for general compressed sensing problems. One, if this is not Gaussian, you have to do some work to actually prove that the least squares solution exists. For that, you typically have to use a matrix Bernstein equality. When you use Gaussians, when you have the Gaussian design, that just happens because the Gaussian is in general position. Second thing we had to prove was that these deviations are not, the infinity deviations were not big. To do that, we just used two facts, which we could go through if you care. One is that basically the norm of lambda has this very nice inverse chi-square distribution. And so that makes most of our life easy. And then the second fact is just using properties of the Gaussian. The second fact is very easy. And that gives us, and that proves our kind of fundamental compressed sensing theorem. Yes?
So in hindsight, this makes it clear why we want to minimize L lambda squared.
Okay, tell me. Tell me, yeah.
Because what's happening is each entry is a Gaussian now with length lambda squared.
Yes.
And then that's it. You want to minimize the length.
Oh, I like that. Good. So we do the proof. So what did we? Lovely. Okay, there we go. So that's a great. Okay, so remember the question before was why are we picking this lambda? Why this solution? Well, when we go through the proof, we just need lambda to be small. So I'm going to pick the least squares one. We want the norm of lambda to be small. I'm going to pick the one with smallest norm. That's nice. That only works in the Gaussian case, but again, that's fine. That works well in the Gaussian case. Actually, you will see this again if you look at these more complicated arguments. Typically, you do have to control the norm of lambda squared. That's actually the thing that you're always controlling because that's going to it kind of propagates in to this matrix. Even when these are dependent, you still you try to decouple these two things and then just bow the norm of this side. Yeah.
An alternative proof would work. It's very similar. You would argue that a t transpose at is close to the identity using, let's say, Joule's Chernoff inequality.
Correct.
And then you condition on that. And you use that.
Correct. And in any of it, what you would do is you now control the singular values of this matrix, and then just let this guy have root s. The problem there is now you have this awful root s that kicks around, and this is why whenever you see an argument that says we assume the signs are random, what that is doing is trying to use an extra Hüfting inequality to basically get rid of that root s. It's cheating. It's cheating. That's all right. We prove things that we can prove, right? So that's really where the Hüfting inequality. Why they always say we assume a random sign pattern. Is really just because we don't, you're considering, you don't have the isotropy that you have in the Gaussian case.
Well, I have a question about the actual theorem. Is there any hope for anything that says, so here you're assuming that x0 has small support, it's S sparse.
Yeah.
This recovers it.
Yes.
So conceivably there could be a theorem that says that any solution to ax equals x0, which is close to being S sparse, is a much larger L1 norm. So that would be a quantitative strengthening of the theory.
So you say anything that's nearly S sparse
Much larger,
has larger L1 norm.
Much larger.
Right, and I guess that typically would be one thing that's close to that kind of characterization is you would say that if you want to say that no vectors which are maybe 2s or 3s sparse lie in the null space of A. And that would also kind of give you a similar characterization. And that is another somewhat orthogonal way of proving this, and that's kind of related to these cones. And what you try to say is that in the null space of A, there are no sparse vectors, or there are no vectors with reasonable L1 norm. These are called null space conditions, and these are closer to the kind of picture I drew at the beginning, where we try to basically bound things away from these cones.
So what is known in this?
There are a lot of different properties of the that. What can we say about the null space? I mean, so let's see. Martin, how much of that are you going to talk about? I could either punt or I could just talk.
I'll talk about approximately sparse vector, which is somewhat related to that. I mean, you can bound the width of the null space over approximately sparse vectors.
I think that's kind of what you end up doing. So what you want to look at is you want to look at the set of, so we have the null of A intersected with the set of sparse vectors. And so what you can do in those cases is use, so there are a variety of ways that actually, I think the one I like the most is by Rudolphs and Verschin, and they can actually bound the norm of these sparse vectors on the null space of A. They use something called Gordon's theorem, which is basically just this Gaussian concentration inequality. Another thing that we can do, if you're looking at a very particular sparse vectors, you can look at the set of this cone idea and look at basically what is the norm of A times V min, where V lives in the tangent cone and has norm 1. All right, so this is like a restricted singular value. And you can also bound this. These tend to actually, what's nice about this is if you use Gordon's argument, what you get is something that looks like square root of m minus the Gaussian complexity of the cone. I always forget how to write a square root g of the cone. And the Gaussian complexity, or the mean width, or proportional to the mean width of a cone. So what's really neat about that is it's kind of tying into ideas that we use in statistical learning theory, where we're really just talking about something which is the kind of this natural complexity measure, and that actually just comes in here. So in the case that you use the entire space, let's say we have an s-dimensional space, this is the Marchenko-Pasteur lower bound on the singular value. If you restrict it to just a cone, you get a different answer, and that will give you this bound, the one that I really wanted. For sparse vectors, this will prove that the number of measurements is 2 times 1 plus epsilon s log n over s, I think plus 5/4 s. We have an argument for this. I think the paper to look at there is by Chandrasekaran. Chandrasekaran. Too many letters. Perillo and Wilsky. We have kind of we actually have a big diatribe, and actually that's kind of what I wanted to close with. We have a big diatribe about how you make this more general. So this was looking at the L1 norm, but really the argument goes much more general. We have any function here which somehow is suggesting low complexity. We can really characterize in terms of basically the width of the descent cone how many measurements are required to reconstruct the particular object you're looking for. And you get, what's nice is that the argument, because it's using Gaussian complexities, you can get very, very tight bounds. We have a little trick to estimate the Gaussian complexity of cones. That tends to be a somewhat simple object to estimate. So that's an advertisement for kind of where this goes. Another place where this goes, you have approximately sparse. You could do, these could be noisy, and you kind of build upon most of these ideas. And so that Martin, when he talks about the high-dimensional statistics, will use a lot of the ideas, a lot of the similar kind of duality ideas to kind of build up those constructions. This simple argument that I was talking about actually does extend too. Just the one we did today extends to a couple other norms. So it basically extends to anything which is a decomposable norm. Decomposable norms was something that was invented by, actually I don't know who to attribute this to. Martin, who invented decomposability? Is that Sahand? This notion of when a norm is decomposable?
Collectively.
Huh? It was a collective thing. So it was a Berkeley idea. You have the idea that basically we had an equation which I erased, which was you had that AT, so A star lambda on one set T was equal to some vector E, and the norm of A star t sub lambda, I'm going to put another star here, is less than 1 on some other space. There are many norms where basically the optimality conditions break down to something like this, where you want to find a solution of a least squares problem and then bound some norm, that's why I put a little star here, some random norm on the orthogonal space to this vector. These norms are just generically called decomposable. They consist of the L1 norm, the ones I know, the L1 norm, the sum of L2 norms, so we have block, like be a block sparse vector, and also the nuclear norm, all have this property. And in all of those cases, in a paper by Candace and myself, we actually, that's where this argument is spelled out. It's in Mathematical Programming in 2012. And we actually go and analyze those things. And you get very nice tight bounds, again, just using this argument. The thing that's nice is the only part of the argument that changes as we change norms, if you have this decomposable property, is this last one. Because this Wishart thing holds generically, because you're always solving this least squares thing. So that thing holds generically, and then all you have to do is understand how to bound these norms in different ways, depending on how the norm changes. Any other questions? Yeah?
So your analysis is based on this characterization of the solution. You introduce this lambda dualism. That's very smart. But are there other ways to just characterize the solution? That's all. First question, if there are, then how do you smartly pick up this characterization?
So again, the idea is that what you do is you use, so all of the techniques I know do the following. You open up convex analysis book and you say, what certifies optimality? Question 1. And there are only a few things. You have KKT conditions. We have the null space condition. I guess there actually are like these other weird constraint qualifications. We can go like the Mangasarian, Fromwitz, something or other, and you go find that. You write down those equations. They will have a random matrix in them, and then you certify that that random matrix actually satisfies the equations. That is the procedure.
You mean basically just try several and
that's right.
Which one works?
Well, I mean, this is mathematics, right? I don't know if we necessarily yet have a way to make this exact. I don't know if we necessarily have a crank that generates proofs for this yet. But that might be a nice fun thing to work on this semester.
Yeah, of course, I just feel there are many ways I could just recharacterize this problem and introduce very strange dual variables and to characterize this solution and which is the best way.
So I think that we're still in that situation. Actually, I think it's another place where we're still in that situation is in, and it's very related actually, is in minimax theory, where we'd like to prove lower bounds on what's actually doable. In that same case, we have a general argument. There are a couple of general arguments, whether they be using Fanel's inequality, using kind of the worst, what's it called, the least favorable prior, using hypercube constructions, but it's still not to the point yet where I can feed it to a computer and they can spit out the proof. Yet. Yeah?
Just one thing. I think for stability reasons you do prefer this least square solution because you can see that in some sense the best dual certificate to use is the one with the least norm for stability reasons if you add noise to it and so on.
Right. I think that's also a good argument. I mean, what you really want is something that sits deeply inside this constraint. So you have to satisfy this constraint exactly, and then you want to construct a lambda that's as inside this as possible. Inside this kind of, you have an infinite set. You have this big subdifferential. You want. Actually, this is kind of interesting. I've never thought about this before, but often the case when you look at subgradient analysis, when you actually look at optimization algorithms, the most preferable subgradient is that of least norm, because that actually is the one that's guaranteeing you that you're going downhill. So it does seem to be that's something that recurs a lot, that the least norm subgradient is almost like a gradient, and hence is kind of the most stable one. Cool. Yeah, so the only thing else that I'm not going to, I actually think that most people should go get coffee, and if anybody really wants to see why this is distributed as an inverse chi-square, you can hang out.
break early, I guess, if people want to hang out and see a little bit on wish hearts and chi-squares. Have a second mini lecture.
So what happens with the moving forward? Then you need this.